Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. I'm here today with a sample problem using Kirchhoff's rules for circuit analysis. I consider a problem like this one a basic example because we're going to end up with only two unknowns to solve for. So using our loop rule twice and our junction rule once, we'll generate three equations, but with only two unknowns, the algebra is pretty straightforward and simple. So our first step when we're using Kirchhoff's rules for circuit analysis is to make some decisions about where we think current is going to be flowing in the wires, as in which direction we think each current is going to flow within the wires. And I'm going to go ahead and set up some reference points to help you more easily follow the steps I'm taking. So I'll put A in my top left corner, B at the left side of the middle wire, C in the bottom left, D in the bottom right, E at the right side of the middle wire, and F in our top right corner. So I think this 9-volt battery is going to drive charge down that left side wire from points A to B, and I'm going to call that current I1. And I think when our current gets to point B, it's going to split, and some is going to flow to the right through the 15 ohm resistor from B to E. I'll call that I2. And then I think the rest is going to continue on from B to C. And what's kind of cool about Kirchhoff's rules is that if you happen to pick a direction for a current that is wrong, you just get a negative answer for your numeric value for the current, and that's your clue that, oh, current actually flows the other way than what I thought. So we've now set up our first junction rule. The junction rule says that the sum of the currents into a junction equals the sum of the currents leaving the junction. It's another way of stating conservation of charge. So our junction rule for point B says I1 equals I2 plus I3. So current I3 is going to continue around through the 6-volt battery and up from D to E. So current I3 is going to enter point E. Current I2 is going to flow across that middle wire through the 15 ohm resistor. So current I2 is also going to enter point E. Well, that means that I2 plus I3 entering point E must yield current I1 flowing back out. And then we would have current I1 everywhere in the top part of the loop, starting at E to F across to A to B. So now we're ready to talk about our possible loops. So the loop rule is another way of stating conservation of energy. So any place that we have energy rising in the form of a potential rise, like a battery, would be like an increase in energy, and then our resistors are going to take that energy back away so that we have a net change over our loop of zero. That's a really complicated way of saying that the sum of the potential rises in a given loop equals the sum of the potential drops. So I'm going to start with an outer loop that goes from A to C to D to F. In that loop, notice we have two batteries. We have both the 9-volt battery and the 6-volt battery, and we're going the right direction for both. The right direction is from the negative terminal to the positive terminal. That's the way we get a potential rise. If we happen to be going from the positive to the negative, that would actually create a potential drop because the energy that our charges are carrying would actually be going to recharge the battery. This is why in your devices, it's so important to make sure that you insert your batteries the correct direction, because not all batteries are made to be recharged, and if they are, we have recharging devices for them, and we don't put them into the device that needs their voltage in order to recharge the batteries. So a little digression there. So outer loop, we've got our 9-volt battery. We have no change in potential going A to B to C all the way till we get to the 6-volt battery, because that's all one wire. So one potential, no changes in energy, no resistors there. Then we get to our 6-volt battery. That's going to be another potential rise. So I'm going to add 6. And there were only the 2 batteries, so I have no more potential rises in this loop. And then we'll continue on. And as noted before, our 2 currents, I3 and I2, are going to come together and reform to make I1. And it's going to be I1 flowing through our 22 ohm resistor in that top branch. So I'm not going to finish solving my outer loop equation just yet. I'm going to go ahead and set up my top loop equation instead. So my top loop is going to go A to B to E to F. So my top loop has only one potential rise, just the 9-volt battery. And then we have the 15 ohm resistor multiplied by its current I2 to get the potential drop across that battery. Sorry, I forgot to mention earlier, that's Ohm's law, right? V equals IR. The potential equals current times resistance. And then we're going to have, again, I1 flowing through our 22 ohm resistor. So we can't do anything further with this just yet. So notice that we have 2 equations in 2 unknowns, which is what makes this a more basic kind of problem. We do have the junction rule. Turns out we're not going to need it to solve for anything for this problem, but I do always like to take the time to set up the junction rule wherever is appropriate in a problem, just for the practice and to help me choose and make those decisions about where I think current's going to flow. So let's come back and finish our calculation here for I1 in our top equation, the outer loop equation. And I got 0.681 amperes, and it is a repeating decimal. I'm going to keep that repeating decimal in my calculator when I finish out my calculations. But you could call it 0.682 if you want to round it at this point. So I'm also going to notice really quickly that 15 equals 22I1, and 22I1 shows up in my top loop equation. So rather than write in 22 times 0.681, which is just going to look more complicated and less pretty, I'm just going to substitute 15 for 22I1. And now I can see I am going to end up with a negative value for my current I2, which means that my current I2 must be flowing the other direction than what I'd guessed. So instead of current flowing from B to E, my current I2 must actually be flowing E to B. I almost wrote the original direction there. So just a quick visual to help you out with that. Our guess for our 2 loops was that we had some kind of big outer loop with current flowing like this, and then we had some kind of top loop like this. But what's actually happening is not going to be that the 9-volt battery is driving the current through that middle branch. It's going to be the 6-volt battery driving current through the middle branch like so. But then we still have our outer loop like so. Thank you for joining me today. I have time slots open for my complimentary family discovery sessions. If you'd like to explore the possibility of working with me, you can contact me at brandyhefflinphysics@gmail.com and we'll set up a time to get together. I'm also open to taking physics problem requests. If you have a problem you need some help with and would like to have solved live, I'll solve the problem for you and create a video. You can send those to physicsproblemrequests@gmail.com. You can also find out more information at my website, brandyhefflin.com, or you can find me on Facebook, Physics Tutor Brandy. I love physics and I love helping you. Until next time.